Question 35 shows a heat engine going through one cycle. The gas is diatomic and the mass stay in place when the pin is removed in steps 3 and 6. Part A asks you to draw the PV diagram for this heat engine, Part B asks how much work is done per cycle, and Part C asks what is this engine's thermal efficiency. So for the PV diagram for Part A, we obviously split this into multiple parts, but we also end up with a cycle. So we're going to have something repeating back to the center. And so from here, I believe that we're going to have a 4-part cycle, as in we're going to have 4 arrows in our PV diagram. Because if we go from 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, we go back to 1, which gives us 4 total arrows, in 1 between each step. In steps 1 to 2, there is a pin holding the piston in place, which prevents the volume from increasing. However, due to the heat underneath, the pressure will increase as a result, meaning that we will have an increase in pressure from 1 atmosphere to 3 atmospheres, but our volume will remain the same at 50 centimeters cubed. In parts 2 to 3, the pin is removed as we continue heating. The piston moves slowly upwards, increasing the volume. However, the pressure will remain the same, meaning this is an isobaric process. So we have an increase in volume from 50 to 100 centimeters cubed, but the pressure will remain the same at 3 atmospheres. In steps 3 to 4, we insert the pin again to keep the volume constant and remove the weight. But nothing changes, so we remain at the same point as we would at the end of B. However, in steps 4 to 5, we cool the gas so that the pressure decreases, but due to the pin in place, the volume cannot decrease, meaning that we have an isochronic process once again with a decreasing pressure this time. The pressure decreases from 3 atmospheres to 1 atmospheres, and the volume remains the same at 100 centimeters cubed. In steps 5 to 6, we remove the pin, and the gas goes back to its original volume of 50 centimeters cubed while keeping the pressure of 1 atmosphere. And steps 6 to 7 is just the return to step 1, completing our cycle. To calculate the work, it's actually very simple. All we need to do is plug in our values into the work equation, which is difference in pressure times difference in volume, which gives us 3 minus 1 times 100 minus 50. Of course, converting our units into joules, we get 10 joules as our final work result. Part C is slightly more complicated and uses the work from Part B in the last step. Efficiency is defined as work divided by extracted heat. To calculate the extracted heat, we need the heat made during the isobaric process and the isochronic process, where both the volume and pressure were increasing. We'll call these heats QA and QB just to help differentiate them. QA will be the isochronic process and is defined as 5/2 nR change in T for process A. Process B is defined as 7/2 nR change in T for process B. Looking at the nRT, we can relate this to the ideal gas law and say that change in P for both A and B times V is equal to nRT change in TA or TB. Knowing this, we can now actually form our equation. Looking back at our original equation with the extracted heat equaling QA plus QB, meaning that we can add the two together and substitute in our P change in V to get Q1 equals 5/2 change in PA times V plus 7/2 P change in V. I actually made a mistake here and wrote down change in P for both. Ignore that. One of these is change in V and one of them is change in P due to them being different processes. Finally, plugging in our numbers for pressure change and volume change, we end up getting a value of 77.5 joules. And taking our work and dividing it by this value, we get a efficiency of 13%. For practice for this type of problem, I recommend looking in the book at more heat engine problems and just generally studying about heat engines, because this sort of thing will probably be commonplace if you were to go into more thermodynamic studies. Anyway, that's all for me for now. Thanks for watching.